This video contains a basic introduction to acids and bases. To understand this material well, you'll want to be acquainted with equilibrium constants, chemical formulas, and chemical reactions. Let's start with some definitions. There are two types of definitions that we work with acids and bases, the Arrhenius definition and the Bronsted-Lowry definition. Arrhenius tells us that acids lose H+ when placed in water and bases lose hydroxide ion in water. And we find that the Arrhenius definition is particularly useful when you're given a formula and you have to decide from looking at the formula whether it's an acid or a base. Something that would contain H+, so from our knowledge of ionic compounds we know pluses, cations are written first in the compound, that the H written first in a compound would suggest it's an acid, and an ionic compound that contains a hydroxide would then qualify as a base, according to Arrhenius. Bronsted-Lowry took things a little bit further and said, well, not all bases contain hydroxides. In fact, what we see in chemical reactions is that acids lose hydrogen ions and bases gain H+. So the Bronsted-Lowry definition works well when you have the context of a chemical reaction to see, is what I'm starting with gaining hydrogens? Is the number of hydrogens increasing? Or is it losing hydrogens and the number of hydrogens is decreasing? So the question becomes, is it an acid, is it a base, or is it neither? Well, in this question, we're just given a formula. And so we're going to rely on our Arrhenius definition. When we look at HBr, we see that there's an H written in the front of the compound, and so that tells us that this is an acid. CH6H6, however, does not have H's in the front of the compound. It has H's written second. This tells us that this is actually a covalent compound and not an acid. It doesn't have a hydroxide present, and so we would say it's neither. So it's not an acid or a base. Lithium hydroxide, hey, look at that. It's got a hydroxide. And it's got a metal, so that tells us that it's present as OH-, so this is a base. C2H3O2 with a -1 charge is our acetate ion. It has hydrogens, it has some oxygens in there, but I don't see a hydroxide paired with a metal, and I also don't see hydrogens written out at the front of the compound formula. So this is neither. C2H5OH looks like it has a hydroxide in it. We see that OH there at the end of the compound, but what we don't see is a metal. And because we don't see a metal, this compound only contains nonmetals. It's a covalent compound and does not contain a hydroxide ion. So this is neither as well. Last, we have NaCN, no H's or OH's in this, so it's not an acid or a base. One topic that you may find yourself having to answer, one question you may have to answer, is how many protons does an acid have? There are different terms that we use to describe them. Monoprotic means I have one H. Diprotic means we have two H's. And polyprotic means I've got three or more H's present. So if we look at H3PO4, we see there's three H's, so we would describe this as polyprotic. HF only has one H, so this would be monoprotic. HC2H3O2 has a bunch of H's. There's actually four total, but there's only one written at the front of the compound formula, and so we know that there's really only one acidic hydrogen. So this would be a monoprotic acid. KOH isn't really an acid at all. We know that because there's no H's written in front. And in fact, KOH is actually a base. This is a base. It's useful to know whether an acid is strong or weak when we get to discussing buffers, among other things. So we need the definition to help us out there. Strong acids will completely lose their hydrogens, and they'll lose them very easily in solution when placed in water. They have large equilibrium constant expressions. So we're working with the idea that we have some kind of generic acid, and when it goes into water, it separates or ionizes into its constituents. And if we were to write an equilibrium constant expression for that. We call it a Ka because it's for an acid. And we would have our hydrogen ion concentration and whatever our counter ion is multiplied together. So if there was a large concentration of products, meaning that the acid had split up a lot, I would have a large Ka and thus a strong acid. Our strong acids, there are 7 of them. You'll want to know these for exams and for being able to do buffer problems easily. Weak acids, on the other hand, hold on to their H's. So they have very small Ka's because in this reaction that we were looking at, mostly they're holding on to the HA. So HA is preferred at equilibrium, and so there's very small Ka's. Bases, our strong bases are going to be the alkali metal hydroxides, so lithium, sodium, potassium, rubidium, and cesium, not francium. All of those compounds, for instance LiOH, would be a strong base. The heavy alkaline earth compounds as well, calcium, strontium, and barium, when they're paired with hydroxide, for instance calcium hydroxide, that's a strong base. If, on the other hand, I had beryllium hydroxide, that's not listed as a strong base, so this would be a weak base. The other weak base that you want to be aware of that's not a hydroxide base is ammonia. NH3 is a weak base. So, are the following strong acids? HF. Well, if you had memorized your strong acids, or if you have the table list in front of you, you'll notice that HF is not included on that list, and so therefore it's a weak acid. An acid with a Ka of 5.25 times 10 to the negative 7th, that's a pretty small Ka. It's pretty definitely less than 1, and so we would say that's also a weak acid. Mr. Strong down here is going to be a little disappointed because even our last one here is also a weak acid, because this is the definition of weak acids. They dissociate or ionize only to a small extent when in water.